OK, so that brings up the question of register renaming. What is register renaming? Hopefully some of you skimmed the Tomasulo algorithm paper that I assigned, because we'll be discussing that and the motivation for that work. OK, so what is limiting our performance in these pipelines, these out-of-order pipelines that we've discussed so far? OK, a couple things. Write after write and write after read dependencies. Let's talk about these. A write after write dependence, you're going to write to one register, then you're going to write to the register again. And in our pipelines that we've talked about so far, you're basically going to stall the pipe while you're waiting for the first write to commit, because we're not able to handle multiple writes in the pipeline at the same time. But these are not fundamental dependencies. So computer architects put on our thinking cap, and we came up with ways to break these dependencies. A read after write, and that also is true for a write after a read. So if you do write to, let's say, register 4 after a read from register 4, well, there should be nothing wrong with that. But if you're trying to execute the instructions out of order, you need to think about that. A read after write is a true dependence because you actually need the data. You need the value to go execute the subsequent instruction. And we're going to call write after write and write after read dependencies name dependencies. And we're going to call a read after write a true dependence that we can't break. OK, so let's look at some example code here and see what can go wrong if you just ignore all the name dependencies. Like I said, they're not true dependencies, so maybe we just don't need them. OK, so we have a different code sequence here. We have a mul, and then 2 add immediates. Let's identify some important things in here. First, let's identify the true read after write dependencies. So I put some circles and some arrows here. So let's take a look here. This writes register 1, and the second mul reads the result of that. OK. Let's see here. This add reads register 4, and the previous instruction writes register 4. So that's a true dependence. We can't break those. We may talk at the end of the term maybe about some ways to break those, but they get pretty crazy. So let's look at the write after write dependence. So the first write after write dependence is here. We're writing register 4, and then we write register 4 again. But in an out-of-order processor, if we try to break all these dependencies, we can see that we're actually writing to register 4 here, and then we write register 4 here. And that's like out of order. Whoa, what just happened here? Well, we said we just broke the dependency. We're not going to stall the front of the pipe on this. So if you go to execute this on one of our out-of-order issue pipes that we've looked at so far, let's say this is executing on the in-order fetch, out-of-order issue, out-of-order execute, and right back in-order commit pipe, we can see that we will write to register 4 in time before we wrote to register 4 here. Now that's going to cause some major problems. We just wrote the wrong value. Oops. And the other one here is a write after read dependence. So here we have a read of register 4. And here we have a write of register 4. And because this add got pulled so early in the execution order, we actually wrote before this instruction had a chance to read the value. And the reason this instruction got delayed was because it was also dependent on a true dependency here. But it's dependent on 2 things. But all of a sudden, we wrote register 4 with the value from this add, and then we went and read it, and we read the wrong value. So we can't just go change and break write after write dependencies and write after read dependencies very easily. We need to think a little bit harder about this. One last interesting thing that happens here, this is kind of fun. We do commit in order in this pipe. But look what happens to register 4. We wrote register 4 here, and then we write register 4 again. And then we commit from physical register 4 to architectural register 4. So we just committed the wrong state also to the architectural register file. So we're having lots of problems with here. It's not just basic things. So what's the solution to this? Well, the solution is we can start thinking about how to add more registers. So at the top here is the same example I had in the previous slide. So nothing new there. But I wanted to compare this to, let's say, our conservatively stalling pipeline from a performance perspective first. So here we have our in order fetch, out of order issue, out of order write back, and in order commit pipes. This is our most advanced one from last time. But it conservatively stalls on write after write and write after read dependencies. And that's drawn here with these arrows. So we can't even issue this instruction until we know that, let's say, these two instructions here, which have something to do with register 4, commit. And then we can go to issue this. Now, this might be a little bit conservative. This might be even a little bit over-conservative. It might be possible to pull this back 1 or 2 cycles, maybe to sort of the point where this instruction does the write back. But one of the challenges there is you can't necessarily track that very easily inside of your reorder buffer unless you have something there that scans for this exact case. And it's not going to save you that much performance either. What I'm trying to get across here, though, is that the performance of this instruction sequence is actually worse. It takes longer than our incorrect, but we'll call ideal case here on the top. So let's do one little change to the instruction sequence, highlighted in red here, and see what happens to our execution. So we took this add, which wrote to register 4, and changed it. We added another register usage here, and now we write to register 8. And lo and behold, it breaks all the write after write dependencies, and it breaks all the write after read dependencies. And all of a sudden, we get to our idealized performance. This is the exact same case as that. But we require another register. Well, can we just add infinite numbers of registers? So what's a con of adding infinite numbers of registers? Anyone have any ideas? So if we're trying to use more registers here, we might use up all of our architectural registers. Can we just add more architectural registers to our instruction set? Yeah, so it takes up space. So if we look at our registers, we could have a larger namespace for our registers. But if we have 32 registers, that takes 5 bits. If we have 128 registers, that's going to take 7 bits. If we have infinite, that will take infinite number of bits. But what we're going to talk about in today's lecture is how to do this in hardware such that you have some more registers in your physical register space, but not more registers in your architectural register space. And this is, I should point out, this is not only a register problem. This could also happen with memory. If you name your memory inappropriately, if you have very small amounts of memory and you try to reuse the memory very aggressively, you can get naming problems in that also. But for today, we're going to mostly be focusing on register renaming. And so I'll define register renaming as we're going to change the naming of the registers in hardware to eliminate these write after write name dependencies and the write after read dependencies. OK, so we're going to be talking about 2 major schemes, and they are mirrors of each other and have slightly different hardware requirements. But they're mostly, when you think of them, they're just sort of logically duals of each other, and there's different ways to think of the same problem. So the first scheme we're going to be looking at is we're going to add pointers in our instruction queue and our reorder buffer to allow us to have different register names in them and not actually just have architectural register names in those data structures. The other option, which is if anyone read the Tomasulo algorithm paper, is to actually store the actual value, the data value, in these data structures, in the reorder buffer and in the instruction queue. And they look very similar if you sort of think about it, and they're going to have the same performance. I'll give you the sort of end of the novel at the beginning here. They're going to have the same performance. They're doing the same thing, but they're slightly different in the mechanics perspective. And we're going to start off by looking at this first one here. We're going to have pointers in the instruction queue in the reorder buffer, mainly because we already have pointers in our design that we looked at last time. This in order issue, out of order, or excuse me, in order fetch, out of order issue, out of order execute and write back, and in order commit design.